Thank you so much. Hi, everyone. My name is Hamid Gorgiara from UC Irvine. Today, I'll be talking about our tool PSan, which checks robustness to weak persistency models. This is a joint work with Wei Yu Lu, Alex Lee, Harry Zhu, and Brian Dembski. Persistent memory is a new technology which provides byte addressable access to persistent data. This new memory provides higher capacity with only 2 to 3 times higher latency compared to traditional data. The benefits come with the challenge of dealing with system crashes, such as power failures, that can cause inconsistency in persistent data. So to use persistent memory, the programs need to guarantee crash consistency. There's a volatile cache system between CPU and persistent memory, and that is problematic because cache lines can be written back to persistent memory in an arbitrary order. For example, this program writes 1 to X and 2 to Y. If X and Y are located on different cache lines, it's possible that Y equal 2 reaches the persistent memory first. At this point, if the program crashes, the data in persistent memory is in an inconsistent state. Modern CPUs provide a special cache instructions, such as CLFlush in x86, to force cache lines to be written back to persistent memory. These instructions have runtime overhead, so it's very challenging to properly use these instructions to guarantee crash consistency with the minimal performance degradations. Researchers have taken 2 primary approaches to improve the reliability of persistent memory programs. First, there is a rich work on constructive approaches that systematically transform a program to use persistent memory. But these approaches only work for lock-free programs, and they may inject unnecessary flush and fence instructions. Also, some of them incur large memory overhead. Second, researchers have developed testing frameworks to find persistency bugs, but they have major drawbacks. For example, some of these tools can only catch bugs that have visible symptoms, such as assertion failures, or they require user annotations to catch bugs that without visible symptoms, which is error-prone. Also, in most cases, when a bug causes an execution to crash, it's very challenging to locate the bugs because the developer needs to manually inspect long execution traces. Our work builds on the notion of a strict persistency, where stores become persistent in the same order that they become visible to other threads. Bugs caused by missing flushes and fences are all eliminated under strict persistency. We can naively implement a strict persistency by adding flush operations after every memory access in the program. While doing it is not practical, a strict persistency can be used as correctness condition in using weaker persistency model. Our key observation is that for most programs, without the need to place flush instruction after every load and store, a program under weak persistency model can still behave as the program under strict persistency. Building on this observation, we propose the notion of robustness based on the behavior of the post-crash execution. I'll use an example with one crash event to give the intuition. Here, the pre-crash execution has 2 threads, and the operations are executed in the order specified by the timeline. As you can see, the post-crash execution reads 2 for X and 3 for Y, which means that the store Y equal 4 and Y equal 5 in T1 and T2 didn't make out to persistent memory before the crash event. This execution is equivalent to the execution under strict persistency on the right in terms of the behavior of the post-crash execution. For simplicity, we assume all stores in strictly persistent executions are persistent. Intuitively, we can obtain the execution on the right by replaying the original execution under strict persistency and having it crash earlier, and then preserving the same post-crash execution. So both post-crash executions have the same traces. The intuition of replaying is captured by preserving 3 conditions. First is read-from relation, that is all loads in strictly persistent executions reads from the same store as the original execution. The second is sequence before relation, which means that we are executing the same program under strict persistency, and we're not skipping any instruction in the middle. And the third is the TSO ordering, that is the order of stores reaching to the cache. This was an example with 1 crash event, but for executions with multiple crash events, more conditions need to be satisfied that the details are in our paper. A program is robust to weak persistency model if for any crash event and any post-crash execution under weak persistency model, there exists some equivalent execution under strict persistency. Robustness is a sufficient condition to ensure that flush and fence instructions are used correctly. In other words, Adding more flushes and fences to a robust program will not change the set of possible post-crash executions. Our tool, PSan, dynamically checks for robustness for programs under x86 persistency model. It reports violations that are caused by missing flushes and fences. Basically, PSan can help developers to understand where flushes and fences are missing in the program and how they can actually fix it. PSan is built on top of Jaru, the underlying model checker. To use PSan, the program has to be compliant with the LLVM frontend, which instruments all memory accesses, cache, and fence instructions. In runtime, PSan controls the scheduler, and it picks an interleaving and a target crash point. Then it runs the program and simulates the crash and the recovery procedure. Our tool monitors both pre-crash and post-crash execution to identify robustness violations. PSan can operate in two modes, random mode and model checking mode, and to explore executions. And in the end, it reports all the robustness violations that it found in the program, and then suggests the corresponding fixes for each one of them. Our key idea is that given a crash event and a post-crash execution under some weak persistency model, PSan compute a set of a strictly persistent execution whose pre-crash execution are consistent with the given post-crash execution. We compute this set of equivalent execution by using potential crash interval. Each potential crash interval is a constraint that specifies where an equivalent execution should crash at. Each load in the post-crash execution that reads from a store in the pre-crash execution updates the constraint. At any point, if the constraint aren't satisfiable, then the execution is not robust. Let's see an example to show the idea here. Here, the pre-crash execution performs 5 stores, and the post-crash execution reads from Y, and then it reads from X. Before the post-crash execution starts, the set of constraint is empty, which means that for any strictly persistent execution, no matter where it crashes, its pre-crash execution is consistent with the initially empty post-crash execution. Now, suppose the first load in post-crash reads from the store Y equal to. Then the set of equivalent executions is reduced to 2 executions because the equivalent execution should crash after the store Y equal to and before the store Y equal 4. Next, suppose the second load reads from the store X equal 5, then PSan adds another constraint that the equivalent execution should crash after the store X equal 5. But as you can see, these 2 constraints aren't satisfiable at the same time, and PSan has found a robustness violation for this execution. We extend this approach to support multi-threaded programs. Since each thread can make different progresses when a crash happens, we would build potential crash interval for each thread separately. However, in multi-threaded programs, different threads can write to the same variable. So we use TSO ordering between stores to the same variable to deduce constraint for each thread. For example, suppose that in the pre-crash execution, X equal 1 is TSO ordered before X equal 2, and then the program crashes. When the post-crash execution reads from X equal 1, we can infer that in an equivalent execution, T1 should crash after X equal 1, and T2 should crash before X equal 2. If we only use TSO ordering to deduce constraint for stores to the same variable, it wouldn't be enough. For example, here, the pre-crash execution has 2 threads, and basically, suppose that the T1 executes the first instruction, and it stops before executing the flush operation. Then T2 reads reads value of 1 for X and writes this value to Y, and then flushes this variable. Then the program crashes. In the post-crash execution, the program reads from X, and then it reads from Y. If the post-crash execution reads from X, we can infer that in an equivalent execution, T1 should crash before X equal 1. Next, the post-crash execution reads 1 from Y, and then we can infer that T2 should crash after the store Y equal R1. So far, these constraints are satisfiable. But this execution is not robust. First of all, X equal 1 commits to the cache before the store Y equal R1. So under strict persistency, X equal 1 is persisted before Y equal R1. And since the post-crash execution reads 1 from Y, it must also read 1 from X. In order to detect such robustness violations, we should also deduce constraint based on the happens before relation. So the main idea here is that if a store becomes persistent, any stores that happens before it should also be made persistent. So in the pre-crash execution, since T2 reads from x equal 1, we know that x equal 1 happens before y equal R1. And now, when the post-crash execution reads 1 from y, we will add two constraints. The green constraint on the right side of the screen is the same as before, but the green constraint on the left is induced by happens before relation. Now, the constraints in T1 are unsatisfiable, and PSan has found a robustness violation for this execution. PSan not only detects robustness violation, but also suggests fixes. Our tool defines a fix as a set of flush interval that covers operations that happens between a pair of stores. In general, there are two cases for robustness violations. The first case is when a most recent load in the post-crash execution reads from a store that is too old to be consistent with a strict persistency model. And the second case is the store is too new to be consistent with a strict persistency model. For the sake of time, we only see an example for the first case. Suppose that the post-crash execution reads from y equals 3. Then PSan infers that the equivalent execution should crash after the store y equals 3 and before y equals 4. Then when the post-crash execution reads from x equals 1, it is reading from a store that is too old, and these two constraints are unsatisfiable at the same time. And PSan reports a robustness violation. The flush interval suggested by PSan starts from the ending of constraint A, the first constraint, and continues until the beginning of constraint B, which means that we need to insert a flush after the store x equal 2 and before the store y equal 3 for variable x. Suggesting bug fixes is more complicated in the multi-threaded context because stores can be in different threads. This is the earlier example that there was a robustness violation in thread T1. If we use the same method to compute the flush interval for thread T1, the flush interval would be empty. In this case, PSan would compute flush interval in other threads. In each of other threads, the flush interval starts from the first operation that happens after x equal 1 for this example and continues until the beginning of thread's constraint. The alternative flush interval is shown in green, which means that we need to insert a flush in T2 after reading from variable x and before the store to y. We validated PSan on FastFair, CCCH, and recipe benchmark that are a collection of data structure for persistent memory such as B+tree. We also tested PSan on 3 real-world frameworks, including PMDK, Redis, and Memcache, and in total, PSan could find 48 robustness violations that 17 of them haven't been reported before. These violations can be categorized into 3 different types. The first type is missing flush and fence instructions. Here's the piece of code from FastFair. And PSan suggests that 2 CL flushes that are marked in green are missing in this program. The second type is cache alignment bugs. Here's the header class again from FastFair. And the problem is that the developers did not carefully consider C++ object layout semantics. Basically, they neglected the fact that a word aligned 8-bit has another 8 bits of paddings in this class. And consequently, the header class is larger than expected, and it causes bugs in the program. Lastly, PSan found 13 violations in memory management code, such as garbage collection. These are real robustness violations, but fixing them require fundamental changes in the design of memory management component rather than just simply inserting flushes and fences. For each of these benchmarks, we compared the execution time of PSan with Jaru, the underlying model checker. In this figure, the y-axis represents time in second, and the x-axis shows the name of the benchmarks. The blue bars and red bars are execution time for Jaru and PSan, and as you can see, Jaru and PSan have comparable running times because checking robustness introduces minimal overhead. To conclude my talk, testing persistent memory program is very challenging, and fixing persistency bugs without any tools is very difficult. As a solution, we present robustness as sufficient correctness condition, and we develop PSan to check robustness in programs to find bugs that are caused by missing flush and fence instructions. PSan could find 48 persistency bugs that 17 of them haven't been reported before. Our tool can localize each bug and then suggest the correct fix for each one of them. PSan is open source, and the source code and the documentation on how to use PSan and how to reproduce our results can be found at the link in this slide. Thank you so much for listening to my talk. Now I'll be happy to take any questions.
How do you capture the post-crash execution?
What do you mean by capturing it?
How do you monitor what happens post-crash?
Okay, so we use so our tool PSan is built on top of Jaru. So what Jaru does is just like run the program, and you just like picks it like a location for simulating the crash, and then reruns the program. So basically, there are like two types of like memory that it is allocated. One part remains as it is. That's going to be our persistent memory, and another part just gets clean. It's gonna be our DRAM. So Jaru is the simulator for us to kind of like simulate the crash, and because we use LLVM, so we have full access to like which part of the memory is which variable are being accessed by the program, which flushes are being used where, so we can do that.
Simulating crashes, yeah.
Exactly.
Okay. So you do not care whether the machine is x86 or ARM, just you see the...
That's a really good question. Yeah. So for now, we just support for x86, but all these ideas can be applicable to to ARM as well. Okay. But different persistency semantics need to be supported.
And do you care what is it included in the persistency domain? Whether it is the RAM, the main memory only, or the weight persistent queue, or
no, we just like care about
because you see just what happens in the post-crash.
Yes, so basically, exactly, we don't care about like if it is a queue or if it's anything. Just like a plain byte that is accessed by the program.
Cool. Thanks.
Of course.
Thank you for the talk. I was wondering if you could comment on whether, like, how applicable this stuff is to, like, more traditional, like, if you're working on a database or something. I understand they have, like, similar issues with, you might commit to, like, a disk sector, not atomically, because your thing splits across, like, multiple disk sectors and stuff like that, and, like, whether you could adopt the tool.
Can you just, like, repeat your question a little bit louder? Sorry.
Sure. My question is, I was wondering if you can comment on, like, how applicable this is to, like, say if you're implementing a database, not in persistent memory, but like if you had a traditional like database like Postgres or something.
Okay. So I think like most of our approaches, like most of this analysis and all the stuff that I show is just like applicable to persistent memory because like they're using flushes and fences basically. But for the general database, there are like, because like for the database now, there's another factor that's being considered important because now we have a distributed system, right? So like that's the completely different story because like for PSan, we just focus on one single machine. And if the machine we are simulating like machine like as like a distributed one, we need to mock all other systems that are impacting our execution. So probably it's going to be different a little bit.
So like more specifically, like I'm just talking about like if you're implementing like say a B tree in your database and just like finding bugs on, if you're, because as I understand it, you have like similar issues with persistent memory. You're saying you have cache line issues. For a disk, you have similar issues with like disk sectors and stuff like that. That's what I was asking about.
Okay, so I think like maybe so like the whole what's it called, like the whole PSan and like our tool is more of like running the program and simulating crashes. So like if for example, if in real database they're using fly disk, it's completely different because that is managed by operating system. You can verify if the write is complete or not, and then it comes with the distributed one. So like it's different than than persistent memory. But we can have the conversation offline to like talk about it more.
Really cool stuff. Let's thank the speaker again.
Thank you.